All right, hello again, YouTube people, and a few people in this room. That was fucking shitty. Let's start this over. Hello, I'm Connor Herndon. I'm with the Society of Physics Students at Georgia Tech, and this is the second lecture in a series on what was supposed to have been Lagrangians, but is now classical mechanics in its entirety, and hopefully I can just keep trucking through all of physics. All right, so last time we talked about the least action principle, or the least minimizing, extremizing an integral, or a functional of some sort. And what we ended up getting is the Euler-Lagrange equation. So if we have some function that is dependent on, you know, a bunch of things, so the positions, the velocities, and then time. I'm going to have shorthand that's going to change throughout this lecture because I don't want to write this every single time. The Euler-Lagrange that we ended up getting is this equation. So what this means is that if we wanted to extremize some integral that was something like this, then this is what this function has to satisfy this relation in order to extremize this integral. So let's have some fun then. So I figured this out while writing the lecture, which I thought was really badass because I didn't know this was even a property of what I'm going to show you, but you'll see. It's some cool stuff. So let's assume that f can be broken up into two parts. One part is only dependent on the positions in time, and the other part is only dependent on the velocities in time. So what we've got is f1, which is a function of the q dots, and f2, which is a function only of the coordinates. So if we have that situation going on, if we were able to separate it through addition like that, then our Euler-Lagrange left-hand side would say this. This is equal to f1 plus f2, just inserting that definition of f explicitly there. So the way that partial derivatives work is that if a function does not explicitly depend on the variable in question, it's 0. So f2 does not depend on the velocities at all. It's only a function of the coordinates and time. So because of that, if you took a partial derivative of it with respect to the velocities, it goes away. So this is 0. So what we end up getting is just d by dt, the partial on q dot of f1. All right, and so for the other side, likewise, if we took the other side of the Euler-Lagrange equation, we have this, and for the same argument, f1 will die this time because it's not dependent on any of the positions, only of the velocities. So this goes to 0, so this ends up just being partial of f2. So what we end up getting for this whole thing is that our Euler-Lagrange equation has now turned into 2(1) equal to this. So in the instance that our function can be broken up into these two parts, one of which depended on the velocities and one of which only depended on the positions, the Euler-Lagrange equation turns into this. All right, so now let's see an application of this, which is going to be really great. All right, so we know Newton's law. I really hope that you do. D by, all right, so you've got F is equal to the time derivative of momentum. And momentum is equal to mq dot, just by definition. It's mass times the velocity of your stuff. So what we can also say this to be is if we just think tricky, a lot of physics is just being real tricky, is that this could actually be considered the partial derivative with respect to some other quantity. So the reason for this, you'll see later. So if we took this partial, if we evaluated it, we end up getting mq dot. That's just what it happens. So we can restate this situation going on here like that. Likewise, we can change f being tricky, because f is also equal to the negative gradient of the potential energy. If you haven't seen that, it's just something in classical mechanics and everything. I'm not going to derive that. And this is equal to, by definition, the gradient is this. I'm just writing it out like that. I'm going to move this minus sign inside of here, just because I can do that with minus signs. All right, good stuff. So we have F equals the time derivative of momentum. So that means that this quantity has to be equal to this quantity if we were following Newton's laws. So the time derivative of momentum all right, whoa, shiggity gack, yeah. So what we can do now is we can just look at what we had derived earlier right here and see that we've got the same situation going on. We've just massaged Newton's equations into something that looks very familiar to what we just derived, this lemma. If we assign this to be F1 of the velocities in time, and this to be F2 of the coordinates in time, because the potential is dependent on the coordinates. So what this means is that there exists some larger function that was broken up into these two pieces. Some larger function that is f of q alpha is equal to this one plus that one. So what we have is 1/2 mq dot alpha squared minus v, because the minus v is in it, q alpha. And what we named this thing to be, this function that satisfies this equation, which is identical to what Newton's laws were and everything, we named this thing to be our Lagrangian. This is what a Lagrangian is. So Lagrangian mechanics does not give you the ability to solve more things in classical mechanics. It just is a different way of looking at it. So whereas solving Newton's equations were vector equations, you have to solve, vectors which are awful, and forces which I don't even believe in. You get to do this in terms of scalars right here. This is what we know to be the kinetic energy minus the potential energy. Both of these are relatively easy to figure out sometimes when forces are not as intuitive. So like I was saying, this does not reduce the complexity of the mathematics that you end up getting, because from Newton's laws for in coordinates, you end up getting in second order differential equations. You get, because this ends up being, you usually have like f is equal to mx double dot, something like that. You get in number of second order differential equations for all your coordinates. With Lagrangian mechanics, you also get in second order differential equations. So the mathematics is identical, but the physics is actually much easier, much easier. Oh yeah, and cool fancy things is that since we named this Lagrangian to be what it is, this implies the existence of some functional that we were minimizing to get to this point, because this thing came from the idea of trying to minimize this functional. And if we see that the Lagrangian is just one of those functions, then there must exist some functional that we're intending to minimize. And this is actually where, this is how you normally derive the Lagrangian going in the other direction. We call this to be action. And if you impose the constraint that the action to first order is 0 like that, if you want to minimize the action, this is Hamilton's principle, then you end up having extremizing this integral, which requires the Euler-Lagrange equation for our Lagrangian. So this is really cool and fancy, because it's going to make things a lot easier for you in life. So what we can do now is solve a very simple system in terms of Lagrangians that you would normally do with forces, and see that you get the same result. This is where it actually becomes very useful. All right, so let's say we've got the only problem that exists in physics. A spring attached to a mass, m, spring constant k, no friction. And we just want to solve it. What's going to happen with this guy here? So we're going to define x equals 0 to be the equilibrium length of the spring. So that way, increasing in whatever direction is x. So instead of having Newton's laws, we're having like f equals minus kx that you just memorize because of Hooke's law. What you can do instead is just figure out what the kinetic and potential energies are, and then blindly put it into the Euler-Lagrange equation and win. So first we have to figure out what the kinetic energy is. So if something's moving, what is its kinetic energy? It's 1/2 mv squared. 1/2 mx dot squared. That's just the kinetic energy. If it were moving, that's what it would be. The potential energy, this is something that you kind of memorize if you haven't already, is of a spring is 1/2 kx squared. It's the displacement. So yeah, these things you can derive from forces, but once you do it, then you can memorize the potential energy of it. And from this now, we can define our Lagrangian to be t minus v, which is equal to 1/2 mx dot squared minus 1/2 k x squared. And now from here, we can just use the Euler-Lagrange equation. So the left-hand side of it, I erased it earlier, but whatever. Oh, you got it there, whatever. dx dot. Okay, so the q's earlier were standing for our coordinates, so now our coordinate is x. So take the partial derivative with respect to x dot. So this is kind of a weird question to ask, because normally you take a derivative with respect to something, not a derivative with respect to dx by dt, which is kind of a strange concept for some people. So what you can do instead is, I think I said this last lecture, is you can rename x dot to be z, and have 1/2 m squared minus 1/2 k x squared. And now for the Euler-Lagrange equation, this is now a derivative with respect to z. And then you set z to be equal to x dot afterward, just to, if that makes you feel better. So what we get out of that is that you get a m x dot double dot, because I'll write it out more explicitly. So you have d by dt in x dot, because that's just the partial of your Lagrangian with respect to the velocity. This term dies out because it's not dependent on the velocities at all. This one just is a regular derivative. And then if your mass does not change, then the derivative of this with respect to time is mx double dot. All right, cool. Now we can do the other side of the Euler-Lagrange equation, where q alpha is now x. And this term dies because it's only dependent on the velocities. And this term, likewise, is just a very simple derivative. 2 comes out, cancels with the 1/2. So you've got negative kx as the derivative there. So now what you do is you set these two things equal to each other. And what you get is mx double dot is equal to minus kx. All right, that was a hell of a lot of work to get back to what we already knew at the beginning of the problem. But this is just more of a sanity check to prove to you that this does actually reproduce Newton's equations. You have not lost any information even though you're dealing with now scalar theory. So there exists much more difficult problems that cannot be easily solved with forces. That's the one I'm going to do at the end. I think it was on people's classmate homework recently. If that homework isn't due yet, don't tell them that I just solved it for you on the board. Okay, now for more philosophy and fun things. So conservation laws are things that we stick to rigidly in physics, because you've got the conservation of energy, linear momentum, angular momentum. You use those all the time, those equations, but they're just laws. Like a lot of laws are just, they're in existence because they've always been true, nobody's found a counterexample, so it's a law. But there's actually ways to derive conservation principles from Lagrangian mechanics. So let's say that we have, again, like how I had before, is that kinetic energy is a function of the velocities in time, and the potential energy is a function only of the positions in time. So then if we were to say this derivative, the partial of the Lagrangian with respect to the velocity, we would get just inserting the definition of the Lagrangian energy here. And since the potential is not explicitly dependent on velocity, it dies, but the kinetic energy stays. So we've got d by d q dot of kinetic energy, and then we can rewrite that kinetic energy as just 1/2 m q dot squared. So that means if you just evaluate the derivative, you've got m q dot. Yes. So that's equal to partial of your Lagrangian with respect to the velocity. So we defined this thing, the thing that I just derived for you, to be the generalized momentum. Because you see in a simple mechanical case, we just have mx dot, and it's what we had previously defined to be, momentum. Very straightforward. But now we can define momentum in a more general way that depends on the Lagrangian rather than like Newton's laws. So if if the Lagrangian does not explicitly depend on some coordinate in your system, then we have the corresponding conjugate momentum is conserved within the system. And the way that we can say that is that we start with just our regular, I'll just erase the alphas, regular Euler-Lagrange equation. And then if we have that the Lagrangian is not explicitly dependent on the coordinates at all, it doesn't give a shit. Like if you picked it up and then you set it down somewhere else, the system does the exact same thing, the dynamics have not changed at all. This would be equal to 0. And what you have now is that, yeah, good stuff. This we had earlier defined to be the momentum, basically, from there. So we can say that d by dt of this momentum is equal to 0, which means that this momentum is going to be some constant, because when you take the time derivative of some constant in time, it is 0. So what we see here is that from the concept of having invariance over translation, we get conservation of momentum. Yeah, I'm going to write the whole damn thing out. All right, so there's a much deeper concept going on in here. It's called Noether's theorem, and I'm not going to cover that here. I'm probably going to cover it on later. But the theorem basically states that if you have some symmetry within your system, some invariance, if you were to do something to your system and the system remains the same, then you have a corresponding conservation law that's associated with whatever you did. So if you have translation, if basically you have an experiment that you're running and then you pick it up and you set it down somewhere else and it doesn't give a shit, then you have a conservation of momentum. That means momentum in that system will be conserved. If you have the same experiment and then you pick it up and you set it down at a different angle, something like that, you twist it around and then run the same experiment, you have conservation of angular momentum because you have a rotational invariance in your system. And one that I'm not going to probably do later, I don't know, maybe, if you have invariance over time, if you perform the experiment now and then you wait 1,000 years and perform the experiment again and get the same results, time invariance, you have a conservation of energy. And that ends up coming out. And it's very cool because in quantum mechanics, these are all conjugate variables, these operators. And this is kind of it's just cool. Physics works out real well. So why don't I just use regular mechanical momentum like we've always seen, in mx dot, just mv. Momentum is equal to mv. Because that's not always the quantity that's conserved in a system. You can have a more generalized momentum. Like in electromagnetism, a regular momentum would just be, mx dot. But in electromagnetism, you have Lagrangian that's given by, yeah. So this is going to be for an electron within some electromagnetic field. So you've got, this is going to be the electric potential, and this is going to be the vector potential, which is associated with the magnetic field. You haven't taken electromagnetism, don't worry about it. This is just something that exists for you. And we can use our definition of what our generalized momentum corresponding to the x coordinate as being the partial of our Lagrangian with respect to x dot. And what you get with this is partial of your Lagrangian with respect to x dot. I'm not going to write that whole damn thing in here, but that's what that is. You put that thing in here, and you end up getting, I'm not going to math either, mx dot, because you get this one, the x dot. This one is not explicitly dependent on the velocities, this term dies. And then you have this term, which is dependent on the velocities, but only the x coordinate comes out of it, because this is a vector scalar product, is the scalar product between some vectors. So you've got this term that comes out. It pulls out the x component of this, and then multiplies it by the charge that was out from it. Yeah, so this means that this is the quantity that's conserved within an electromagnetic system, not just regular mx dot. And that causes some philosophical problems, I guess, if you take an E and M. But what we see from classical electrodynamics is that the E times AX ends up being the x component of the electromagnetic linear momentum. So that's some fancy stuff. Yeah. So now for more applications, because that's what's actually useful about Lagrangians in this whole lecture series, so that way you can use it in your classes, because they don't teach them to you for some reason. So when you're doing a classmate homework, you can actually pull out Lagrangians instead. Much simpler, much easier, much more straightforward. So what we can do first is another very simple problem, and then I'll do a very difficult problem. So we're going to do a mass falling in an gravitational field. So if we name this direction to be y, then our kinetic energy is equal to 1/2 mv squared. It's just my dot squared. That's kinetic energy. The potential energy of something that's a height above the ground. What did I say? Y? Yeah. So if y is equal to 0 at the ground, and this increases the y, this distance here, the potential energy is just mgh. It's the height above the ground, mgy. So what we can do is now we can define our Lagrangian to be kinetic minus potential energy. And now we can just blindly throw mathematics at it, because that was the entirety of the physics of the problem. That's what makes Lagrangian so wonderful, is that normally you would have to think a little bit more, but now you don't have to. You can just math real hard, and you get the answer. All right, so this is the Euler-Lagrange equation. Just that's at least one thing that you're going to have to memorize, because it's so beautiful, works so well. This term is going to be equal to you just pull a 2 out front, and then my dot. And then this term dies because it's not explicitly dependent on the velocities. And then this is also a time derivative that was out front, so you get another dot on that. I hope that makes sense. I'm kind of running through math pretty quickly. All right, whatever. So that's for the left-hand side. For the right-hand side, you have partial of your Lagrangian with respect to the coordinate. And that is going to be, this one dies because this is not dependent on the coordinates, only the velocities. And this term ends up being minus mg. So what you end up getting is that mx double dot is equal to minus mg. So like I said before, no, you don't get anything new. That's now Newton's law, and you knew that from the beginning. So again, we're just confirming that we do receive the same results in the end. So now we're going to try a system that's just a bitch. And you're going to see why this is so much better. And because of that, I don't have the notes for it. I'm going to try to solve it in real time for you. So please, if there's anything wrong, please tell me, because this is going on the internet. All right, so look at this abomination. So we've got the ground, and then we've got this hoop. Get used to this problem, because I think you have to solve it like 4 times throughout your physics career in undergrad. I remember seeing this on so many homeworks. And so imagine it's like a coin that we put on a table, and we're spinning it. So this thing is spinning some angular velocity omega. All right, so this thing is spinning around on the ground, and it's also a hoop. And on this hoop, we have a mass that's constrained to move along the inside of the hoop. So this thing, if it were just a hoop, it could just move around, do all sorts of things. But we're also spinning it now, so this mass can move in all different wonderful directions. So this, trying to solve this with forces would be very difficult, I believe. I don't want to do it. I think if you were in class mech, I think you just did do it. So we're going to use Lagrangian instead. So we're going to define some coordinates here. If we have theta there, and I think that's the only coordinates that you'll need. Yeah, good stuff. So, we all talking shit?
Yeah.
Oh, all right, fine. I can't take that. My heart's too gentle. Kinetic energy is so if you know kinetic energy of rotation, it's just it's 1/2 mv squared. But now your velocity is dependent on an angle as well. It's 1/2 m. If this distance of the circle is r, then you have r squared theta dot squared. That's just with the kinetic energy of this mass where it's to spin around this hoop. But now you also have another kinetic energy, which is dependent on the hoop spinning its own damn self. So the hoop is spinning around. So this mass is not only moving in this direction around the hoop, it's also coming in and out of the board. So its velocity here is dependent on its distance away from the center of the hoop. In that distance, this is going to be r sine theta, this distance. So it's the same exact formula as this is 1/2 m r dot squared, or r squared theta dot squared. We also have to take into account this distance. So now it's 1/2 m sine squared theta. Yeah! All right, so that's our kinetic energy. God help me, I hope it's right. So we've also got a potential energy associated with this system. So the potential energy is going to be measured as the height above the ground. So this can be expressed as, this is where you just have to kind of think real hard. So when theta is equal to 0, you have to have the lowest amount of potential energy. And as theta increases, you have to get up to r first, and then you have to go up to 2r. So what you could say is that you know that there's going to be a sine or a cosine or something in there because it's rotating and everything like that. Cosine, when it's 0, this is equal to, that's equal to 1, so there's a 1 minus 1 is 0, so the potential energy is 0 down here. When it's pi over 2, it's going to be at this location, so it's 1 minus 0 mgr, yeah, good stuff. And then when it's pi, all the way up here, it's equal to minus 1, so that turns into 2, so it's 2 mgr, because this distance is now 2r. And potential energy is mg times the height. Yeah, good. So now we have a Lagrangian. Yep. Yeah! And now we can just blindly do math. So that was actually pretty difficult, but it's probably much, much simpler than if you tried to do the forces associated with it, I'm sure. I don't even want to think about it. So we can just do the partial of your Lagrangian with respect to theta dot. And that's going to be from this term, you've got mr squared theta dot. Yes. This term, yes, good. No other terms are explicitly dependent on the first derivative of the angle, so they die. And then if we take the time derivative of that, this is just mr squared theta double dot, because m and r are not changing. That would be really bad. And now for the other side, well here, I'll just write out the Euler-Lagrange equation so you know what I'm doing. This is what I'm solving, so the left-hand side is what we just have there. So if I'm solving for the right-hand side now, this is going to be, the first term dies because it's not explicitly dependent on any of the theta components. This term is going to be a derivative. So you've got, yes. So sine theta, cosine theta, yes, yes. And then you also got, yeah, we're good, yeah? Yeah, okay, good stuff. You've got this term as well, which is, what was that? Oh, you're telling me the answer, don't do that. mgr sine theta. Is that a minus those? Yes, yes, minus, it ends up being minus. Good, excellent. I hope this is good so far, because now we're going to set these bastards equal to each other. mr squared theta double dot is equal to m omega squared r squared sine theta cosine theta minus mg r sine theta. Yeah! We divide by mr squared on both sides. It's equal to, well actually, before I do that, I think you can show this as like a torque in some way, but I don't want to do that. This is going to be the same equation that you would have derived from Newton's laws had you wanted to do that. Oh man, I'm feeling like there should be a minus sign in front of this.
I feel like there should be.
You think there should be as well? Yeah, okay, now we have to find where this minus sign went. Or not though.
Actually, so when we solved this problem just now, you got minus omega squared and then plus the g over r. So both those signs are opposite.
Oh, oh, good. Wait, where did I do that?
Wait, is that how we did it?
That's not the same equation that we had.
Well, first when
No,
you translated v into your Lagrangian, you forgot to subtract it. No, wait, no, never mind, you did.
Yeah, that's what I was
Oh no, wait,
thinking.
no, it was correct as it was. Because when you move it all over to one side, then you get the proper signs.
Interesting. Oh well, let's keep trucking. Confidence. This is what I should have done the notes beforehand, but I'm not, because I'm a Viking. Okay, so now we can take asymptotics to actually see if we have something correct here. So if we, if theta were very, very tiny, like damn small, then this term goes away, and you've got the, yeah, this is wrong. Oh well, I'm going to say, You get the idea of what Lagrangian mechanics is about. I'm never going to do this again, trying to solve the problem on the board for you in front of you. It's going to be terrible. What we get here is, I claim this to now be the answer. I don't care what reality states. There's probably some actual other answer is the real answer, but this is now our answer because we're in this room and I'm the boss. This is how you can solve a problem using Lagrangian mechanics. You first get the kinetic energies, you get the potential energies, you just put it into a Lagrangian. You have the kinetic minus the potential energy, and you just do this. You don't even think, just nothing. Just memorize how the potential energy of some things is. So for a spring, it's 1/2 kx squared. You know, for height on gravity, it's like mgr, things like that, mgh. And then you just plug it in, and that's really it. And then you just solve the Euler-Lagrange equation. What you end up getting is hopefully a correct answer, but sometimes not. But you should mathematically be getting the correct answer all the time, and usually it helps you out in the end. So that's it for today. I tried to do more examples rather than math and philosophy sorts of things because I should be teaching you something that's useful. So hopefully you do learn something by the end of all of this. So for the next lecture, do you people want more math? Fill this up, like what does it mean kind of thing? Or do you want actually how to use these more with pre-written examples? Examples?
I like a little bit of both.
Okay. Okay, because otherwise I was probably going to go into Hamiltonians very soon. So they're just like we generalized Newton's equations to Lagrangians, you can generalize Lagrangians to something called Hamiltonian. And it's a very natural framework to work in. Because the Hamiltonian is sort of like an energy. It's not always an energy, but it's more general than that. And it lets you, instead of solving in second-order differential equations as you have to do with Lagrangian mechanics, you can solve 2 in first-order differential equations. So you double the amount of equations you have to solve, but you now reduce the complexity of the differential equations themselves from second order to first. And that makes it nice. Yes, that's what.
When you do the Hamiltonian, can you do also talk more about the philosophy of it?
Hell yeah!
Yeah.
No, I absolutely. If I could, I would just be talking straight philosophy. It'd be so delicious. But you really should be learning these things because Lagrangians are extremely useful. You're going to be expected to know them in graduate school and expected to know them for the GRE. And not only are you expected to know them, they're very useful. They're the most useful thing. Like, I don't even know how to write a force anymore. I have no idea because Lagrangians are just so useful that I've forgotten everything before. Yeah, so that's it. Are there any questions? Very cool. Then thank you very much. Yeah. Which is like a pendulum. So that means that, yeah, oh, and also omega small. Let's say we're not spinning it, and then there's also theta is small oscillations around the bottom. There's a pendulum. So fuck yeah, that's the best. Then as you increase big omega, life gets bad. Yeah. Man, I should be more confident. That's fucked up.
I think I have too many subscribers.